Hello and welcome. Today what we're going to go over is we're going to be going over how to write two parts of your fruit fly lab report. One is the interpretation of results and the other is the sources of error portion of your results. For this, I'm looking for two distinct things for your sources of error. I want you to talk about Hello, welcome. Today we're going to be going over your fruit fly lab data. So there are two areas on this lab report where I want you to talk about your data. One is in the interpretation of results and the second is in the sources of error. So let's go into those calculations that I want you to have in your lab report. So first off, for your interpretation of results, you are going to have to tell me the mode of inheritance. So I'm going to work through this one with you together just so that it makes sense to you so you can calculate those expected values that you're going to need for two other calculations that we're going to do for your percent error and for chi-squared. So what you're going to do for the interpretation of results, determine the mode of inheritance factor, you're going to look at the F1 data and you're going to look to see if one trait was hidden. And if one trait was hidden, then we're going to say that's recessive. And then the other one that was doing the hiding or that masked the other is going to be the dominant trait. So if I look here with white and wild eyes, well, I started with a wild-eyed male, and now the male only has white eyes, and then the white-eyed female, now the female has wild eyes. Well, I'm going to say that if I'm looking here, that wild seems to be dominant over white eyes, but this one kind of has something funny going on where it doesn't look like traditional dominant recessive that you would see in Mendelian crosses. So I'm going to hold off on the wild eyes. I'm going to look at the next two. Here I have a wild and sepia eye parent, and only the offspring have wild eyes. Same here. I don't even have wild-eyed mentioned, but this plus means wild. So looks like they have wild everything, wings and eye color. So I'm going to say that wild eyes is dominant. And because sepia was hidden here and sepia was hidden here, I'm going to say that sepia is recessive. For white eyes, again, this one was a little bit different, but if I'm already saying that wild is dominant, I'm going to say that white is recessive, and then I have a hinkling, that I have a guess as to what this white eye is going to be besides just simple dominant recessive. So I'm going to say that white is recessive. For normal wings, normal is the wild, and again, if I'm starting with vestigial and wild, I only get wild. So normal has to be dominant, and vestigial is going to be recessive because it was hidden. Okay, next, is it autosomal or sex-linked? So that's what I think is happening here with this. If I have my white-eyed female, I know she's going to give her X chromosome to the males, but remember, females can also get, or do also get, an X chromosome from their dads. So I'm going to say that white eye is X-linked, and that the rest of them are going to be just autosomal, that there is no difference in gender for the second and the third cross. So then what I need to do, knowing this information, I am going to have to figure out those expected ratios still as part of the interpretation of results. So what I'm going to do is I'm going to total up all of the class data, and I end up with 221 of those flies. And I will need that a little bit later. But in order to predict percentage about how many I would expect, I'm going to follow that model of X-linked recessive. So if I have a white-eyed male and a wild female, well, from that F1 cross, the wild female would have to have, I'm just going to back this up a second, would have to have one of the dominant alleles from dad and one recessive allele from mom. So she is going to have this genotype. And again, since it's sex-linked, I need to use my X chromosomes, 2 X's for the female. So this was the X-linked dominant, and then this one's the X with the recessive. So she's heterozygous here in the F2 generation. For males, since they are white eye, this is going to be his genotype. He is going to have a recessive allele attached to his X chromosome. Then I fill it into the Punnett square. I'll put mom at the top and dad at the side and fill it in. And then these are my resulting offspring. So I'm going to use this to explain my predicted ratios. So I would predict that for wild male, which is here, that there is 1 out of 4 boxes, or 25%. For wild female, this is here, there are 1 out of 4 boxes, so 25%. White-eyed male here, 1 out of 4 boxes, 25%. And white-eyed female, 1 out of 4 boxes, or 25%. So then this is what I'm going to include in my interpretation of results for that first cross. So you're going to need to do this for the sepia eye cross, and then for the sepia and vestigial-eyed or vestigial wing cross. The next section that's a little bit different are your sources of error. You need to tell me 3 different things. One, you just have to tell me what that regular error was. So what would have went wrong in your lab? A lot of this is probably due to the counting or the putting the flies into the chamber to knock them out and anesthetize them. So tell me what kinds of things went wrong that you could have improved. Second is percent error, and the third is chi-squared. So how do you calculate percent error? Percent error is observed minus expected divided by expected times 100. So to fill it in, I am going to have to figure out what my expected value is. So you can calculate your expected value by taking that percentage that we figured out in the last slide, and you multiply that by 221, which was our class total. So 25% of 221 is approximately 55. So it's going to be the same for all of them because they all had the exact same predicted percents. For my observed values, these are the ones then that you got from lab. So this is your actual lab data. I observed that for the wild males that there were 72 of those in your class total data. So your observed value is 72, your expected value is 55. You're going to plug that into the equation. So 72 minus 55 divided by 55 times 100, you will end up with about 31% for your percent error. So that's for the wild male. You need to do this for the wild female, the white-eyed male, the white-eyed female for this equation, for this cross. And then you need to do this as well for the other 2 crosses. But just the F2 data. Just use the F2 data. The chi-squared is a little bit more complex. The difference between chi-squared and your percent error is that the chi-squared adds that statistical validity. So it's going to be able to tell you if your 2 data points, your observed and expected data, if that is going to be significantly identical or if it is not. So for this, you're going to use this equation here. It's very similar to the percent error equation, but I'm going to show you how to set a table up, and the table might be an easier way for you to calculate the chi-squared value. But what it is you take the sum of observed minus expected squared divided by expected. So you would do one of these calculations for each of those groupings that you have. So my observed values, again, those are ones that just pulled directly from the class data for the total data for that cross, that F2 cross. My expected values in this case are not going to change from the percent error. So again, I still expect this many out of 221 to be these different phenotypes. So here's a table that you can use to plug this in. So I just have up at the top the observed minus expected squared, and the observed minus expected squared divided by E. So I just take 72 minus 55, I get 17. 17 squared is 289. 289 divided by E, which is this, 55, and I get 5.25. I just round to the nearest hundredth place. And then once I figure that out for all of them, then I'm going to end up with my total. My total is going to be my chi-squared because I summed or added all of these values for each of the groups. So now what do? Now that you have your chi-squared value, you need to compare it to what we call the critical value. So again, our chi-squared is 8.05. You're going to use this table or a table similar to this. I'll post one on the Fly Lab where this is located to figure out what the critical value is. In this class, we're going to be using the probability level of 0.05, meaning that with 95% certainty, we can say that those two values are significantly identical to one another. So how do we know, though, if I use the DF 1, 2, 3, 4, or 5? Well, the DF stands for degrees of freedom. To calculate that, you just take your number of choices minus 1. In this case, we had wild-eye male, wild-eye female, white-eyed male, white-eyed female. So we had 4 different choices. So our degrees of freedom in this case is going to be 3. So if I look at 3 and a probability of 0.05, my critical value is right here. My critical value is 7.815. What does that mean? Well, now you compare the chi-squared to your critical value. If your chi-squared value is less than or equal to the critical value, then you accept your null hypothesis, and that means that your values are significantly identical, and that the only difference that you might have is just due to random chance, but that there is no statistical difference between those two values. If your chi-squared value is greater than the critical value, then you reject the null hypothesis and the values are not significantly identical. Or you could say that there is a significant difference between those two values. So in our case, since 8 is greater than 7.815, our values are not significantly identical, that they are significantly different. And that could have occurred from one of two factors. One, that there was error involved, that the error involved in terms of counting the flies, maybe not having enough flies, maybe killing or releasing flies would have altered our data. Or there could be a possibility that our inheritance predicted pattern was wrong, and then we could do the same thing again. I'm going to be pretty confident that our inheritance pattern is correct, and I think that the lack of us accepting our null hypothesis is because of error that might have involved in this lab. I hope that this was helpful. You can pause, hopefully slow down, rewind the video, so that you can understand how to calculate percent error and chi-squared, and then what chi-squared means. If you have any questions, please let me know. Have a good day.